likely. Yeah. Okay, so our last module for chapter 17, following on from limits, when is a function differentiable? So our learning intention is, once again, I've updated it on the thing, on my version, but for you guys it was a little bit outdated. Your learning intention today is to understand the difference between continuity and differentiable and how they can both apply to functions. So remember, we defined this idea of continuity right at the beginning when we defined limits. Can anybody remember what is the definition of continuity? How do we know if a function is continuous?
If you're looking at a graph,
Yep.
you have to draw it and take the pen off the page that it's not.
Right. So when we're looking at the applied side, absolutely. Now, what about from the pure math side of things? How can we use algebra without drawing a graph to determine if a function is continuous? Do you remember when we looked at limits, left and right limits? Does that ring a bell?
Like negative.
I remember what we were talking about, but I forgot how, what kinds of things.
If the left limit doesn't equal the right limit, then it's discontinuous.
That's right. Or we have a discontinuity at that particular x value. So we're going to be building on that particular aspect of limits and continuity today to ask ourselves when a function's differentiable. So a function, really just one, I wanted to keep it as succinct as possible. A function is differentiable everywhere where the graph of the derivative is continuous. All right, so that means if we can determine the derivative and then we run this continuity test for it, if the derivative is continuous everywhere, then the graph is differentiable everywhere. That is, we can find its derivative at all points. So, how can we apply this to some problems? Let f be this hybrid function where x is greater than or equal to 0, it has the value of x, but if x is less than 0, it has the value of negative x. Sketch the graph of the derivative for a suitable domain. Okay. So let's just write down what our function of f is. I know it's listed above, but I just want to have this contrasting written by hand. Okay. Where x is greater than or equal to 0, and x is less than 0. Alright. Our derivative of our function f is going to be Can anyone help me out with the first part? 1. Yep. And the second part? Negative 1. Okay. So that part is pretty straightforward. What about the domain here? What does your intuition tell you about what the domain should be? X is greater than 0. Greater than or equal to?
No,
or just
greater
greater? Okay, why have you said just greater than?
Because if it equals 1, then it can't be 0.
Right. What about the second?
X is smaller than 0.
Right. So this is going to become a bit more clear in a second, but the difference here is that this has changed. Now let's graph the derivative to then have a justification for why this has happened. Now, unfortunately, I can't use a ruler on this guy, so I'll just draw it as kind of as straight as possible. Yeah, my iPad is a guy. His name's Brock. All right. So we've got our graph of x against a derivative function, or f dash of x. Now, we found out that for x values greater than 0, we have a value of 1. So for greater than 0, we have a value of 1. And then for x values less than 0, we have a value of negative 1. Alright. So, let's go back to our original statement. A function is differentiable everywhere where the graph of the derivative is continuous. So this is the graph of the derivative. What happens as we approach x equals 0 from the left and the right? The points don't meet, do they? So what that tells us is we have a discontinuity at x equals 0, and what that means in practice is that this function doesn't have a derivative at x equals 0, which means that we cannot make this x greater than or equal to 0 because it doesn't have a derivative at x equals 0. So let me just put that there. As f of x, f dash of x, isn't continuous at x equals 0. Okay. Have we got determining the derivative function, just the first part, so f dash of x for example 17g2. Have we got getting the derivative function for the second example? Just while I wait for the last few people to jot this down.
2x plus 2.
Okay. So for the function with the following rule, find f dash of x and sketch the graph of y equals f dash of x. So we're finding the rule and then we're actually providing a graph again. So instead of writing it all down again, I'm just going to leave the function f of x here and then we'll just write the derivative underneath. Hopefully you obtained as a derivative as 2x plus 2 and 2. Now the point where those domains meet is at what x value?
If x is larger than 0.
Well, the point where these two graphs reach the common x value would be x equals 0. So at x equals 0, is there a discontinuity? Can we see? Just without having to graph this graph? Is there a discontinuity at x equals 0? No? So if there's not, could we define the domain here? Yes or no? As in, before we had to kind of draw the graph first? Well, we've just done a very quick algebraic test. Using what we know about limits, substituting the limit of this guy from the left hand, or from the right hand side, and then from the left hand side. Does it reach the same point?
Yeah.
Okay, it doesn't have a discontinuity, which means that the x equals 0 is included this time, because there is no discontinuity. So I'll outline that once again, because that's the kind of the trickiest part of this aspect. We've got our graph, once again, of x and f dash of x. So from x values that are less than 0, we have 2. And then 2, and then going up with a gradient of 2, including our y-intercept of 2 here. So that would be our graph. And we could say that, you know, you don't need to provide this part, I'm just trying to outline that as f dash of x is, so is and not is not, is continuous, at x equals 0. So this wasn't changed as in the previous one. And that's all about, that's all I wanted to cover for today. So for those of you who didn't get the first graph, I'll put that onto Style in just a minute with the video as well. But hopefully you've identified the difference between continuity and differentiability. Just from these two examples. Thanks everyone.